Okay, great. So, hi everyone. Let's start our lecture. Today we will discuss recurrent neural networks. So, the things are getting even more interesting. And previously, so last lecture, we discussed the expressive power of neural networks in general. Then um, we discussed a lot of details about two-layer neural network implementation in PyTorch. So with PyTorch models and classes, we were familiar with cross-entropy loss for binary classification task, and again we discussed in details the backpropagation algorithm. Then you need to compute all the gradients from the loss function with respect to the parameters of your model, and then you usually update the values of your parameters with these gradient values and some learning rate inside. So you want to go into anti-gradient direction to decrease loss function, to have value of loss function as close to zero as possible. And today, so why do we need some other architectures except the classical feed-forward or even convolutional neural network? But of course, we will discuss what is it convolutional neural networks in the future. But today, we want to understand the recurrent ones. So the disadvantages of feed-forward neural networks are this one. So the first is that your input is always fixed dimensional vectors. For example, it may be two-dimensional images, or maybe some three-dimensional structure or one-dimensional vector of features, but you need to specify the sizes of your input before training. And the output is also a fixed dimension vector. So your result has fixed dimension too. For example, it may be the 1,000 probabilities of all the classes or for your images. And you cannot get rid of these limits of the neural network in classical scheme. And the other disadvantage that you always done the fixed number of computational steps. I mean that you are performing forward pass, and then you count all the gradients in backpropagation pass, in back pass, but then you update weights, and every time, so between input and output, you have only a fixed number of computational steps. So it defines the whole architecture of your network. You cannot change it during inference, so the forward pass, or during backward pass. And that's why we need some other architecture, some other schemes. And the first solution of this problem is so-called recurrent neural networks. So on this picture you see different variants. So it can be one-to-one correspondence, so between your input and output, and this is very similar to classical neural network, but sometimes you are using one-to-many or many-to-one correspondence, and so on. So let's discuss the examples of different tasks for different recurrent networks. If you use only one-to-one scheme, then it is called vanilla neural network, and this is very similar to usual classical classical linear layer, for example. Yeah, but when, for example, you want to describe your image, it is called image captioning. Then for only one image as input, you want to generate some number of words. Yeah, so the description of picture, and you don't know the exact size of your final sentence. So you need to generate something and to stop at some moment. Yeah, and recurrent neural networks can do it for you. Of course, sometimes you want vice versa. For example, in the sentiment classification task, there your input is sentence, for example, in English, and the output of your model is simply binary evaluation of the sentiment, or not binary, maybe float evaluation. Yeah, so between 0 and 1, and this is the many-to-one correspondence. For very understandable and general machine translation task, you want to translate the sentence, for example, again from English to Greek language, and of course the number of words inside could be different, so in different languages, and even your input is different by size, so you can translate long sentences or short sentences or even one word, and you want to do it with one and the same model. You don't want to retrain or train different models, so you want to use one and the same model for any task. And yeah, so for many-to-many correspondence, it is possible to solve the video classification problem on frame level. It means that your input here is sequence of frames from some video, I don't know, 3, 5 or 10 frames, and you want to predict something, or you want to transform your video input to the video output. Yeah, so each frame is an image, two-dimensional image, and your model will transform and do something with your video, or maybe perform classification tasks. So each step will be or again binary answer. Yeah, so if you have some object on your frame, for example, or not. Okay, so this is the general scheme and architectures, and of course you can process fixed input with recurrent neural networks too. So if you have fixed two-dimensional image, then you can go pixel by pixel, yeah, from left to right, from top to down, and use this model for classical task of object recognition or classification or so on. And actually, you can even generate the output with recurrent neural networks. So this is the link to the paper, and you see the GIF image with result. So really, the model draws different pictures, different house numbers, even colored house numbers. Again, it goes line by line, yeah. So for example, from left to right, from top to down. But it is possible to generate some images in recurrent style, in recurrent way. Okay, now let's discuss the network scheme for vanilla recurrent neural network. So this is the general approach. Yeah, your input is here, so axis from left to right. Yeah, and your output. So for each input x, you generate some output y. So this will be raw score in the future, but now it's simply some number. Yes, so for or vector of numbers. And inside this block, you always perform one and the same operation. So inside this block, you have some hidden state vector ht, it changes with iterations, but the rule of updating HT and generation the answer is the same for all blocks. So let's write the formula for recurrent neural network. Your input is always the xt vector or number, and the hidden state from the previous step, yeah, ht minus 1. And here some function fw, which is parameterized by parameters w, gives you the next hidden state ht. Yeah. Oh, the scheme is very simple, and the only question is what function can we take as f. Yeah. So let's guess. Yeah. So if we want to create the simplest model with this formula, yeah, how can we combine two, let's say, vectors, one-dimensional vectors, yeah, ht minus 1 and xt, with some operation to one new vector ht with the same size as ht minus 1. So this is hidden state. We should change it, and maybe the simplest formula is well-known linear layer. So for vanilla recurrent neural network, we use very simple function. So you see, we multiply xt with matrix wxh, matrix of parameters, and this is dot product, so this is matrix multiplication of two-dimensional matrix and one-dimensional vector. Yeah? So the result will be again one-dimensional vector with different size. And you see index here, so from x to h. So the size of result here is length of h. Yeah. Then we multiply the second input ht minus 1 to the other two-dimensional matrix with parameters whh. Yeah. And again, the result will be some other one-dimensional vector with the same size as right hand side, and then we apply, of course, activation function. In classical scheme it is tanh, so the hyperbolic tangent of the vector. Yeah, so this is component wise activation function, and your new result, so the result of the hidden state on the next step is ht. So then you can go to the next step and combine ht with xt plus 1, so with the next input. And so also you need to generate the answer, yeah? And for this you need third matrix. So this is again the simple dot products of matrix multiplication of vector ht with matrix w, so from h to y, and the result on current step is yt. Yeah. Great. Let's go on to the actual picture of what is going on at the and very simple example of predicting next character in the word or in some other data set. So imagine that you have very simple one word problem. So the data set is the word hello, and that's it. And you want to model this data set. Yes, so you want to train your model on the word hello. And you see, we have only 4-letter dictionary, so only 4 letters, H, E, L, and O. And for each input, so this is input layer, we need to encode our characters to some vectors. And here we use so-called one-hot encoding, which gives you simply binary vectors with with 0 and 1s, and only one component equals to 1, and the number of this component is the number of letter in our dictionary. So the H is first letter, that's why we have 1 here in the first component. The E is second letter, then 2. L is third letter, so that's why we have only on the third non-zero component for this input. So we can multiply all these binary vectors on one and the same matrix W x H, yeah, and add the result of multiplication, the vector from previous, so the hidden state vector from previous step, multiplication with matrix WHH, yeah, and the result, so the 10H of this sum will be next hidden state vector, okay, each time. And here you can ask what is the first, the 0 H0 vector, yeah, H0 vector. We can simply put all zeros here, so the input for first letter will be simply 0 vector multiplied by the matrix, so it means that we don't change the result of multiplication, yeah, WXH and the encoding of H character. So, and here we change the state of the recurrent neural network, and each time we predict next character. So we want to predict next character. This is our task. And the result of prediction, so you see here we again multiply hidden state on the matrix of parameters W, H, Y, and vector Y. So here you see it has 4 dimensions, so 4 components. Why here? Why do we need 4 components? Because our answers are among four letters. Yeah, so we have only 4 letters to predict, and each component of this vector is the score for each class. Yeah, that's why if we start with letter H and we want to predict the next letter E, then the ground truth answer is so the vector with second, the maximum in second component. It should be so. So we want to train our model to predict E after H, and that's why here we want to increase the second component. So for next step, for letter E, we want to predict L because it is word hello, yeah, L goes after E, and that's why the third component should be should be the greatest, yeah, from all other. And so in general, when we solve the prediction, the forward pass task, of course we apply softmax to the values of the y's, so the 2 values of the scores, to transform all the real scores to the values, to the probabilities, yeah, values from 0 to 1. And then we simply, calculate the loss function, which is cross entropy loss here, because essentially we solve the classification task, yeah, because each time we want to predict 1 letter out of 4, it means we want to predict 1 ground truth label for among 4 classes, yeah. So this is for word hello as trait, and actually that's it. So this is the character level recurrent neural network. We here, so based on our loss, we can calculate all the gradients with respect to the parameters matrices and update values of the parameters to improve our loss, to decrease our loss and to improve the quality of solution. Yeah. Let's go on to the code. Now I want you to show the same recurrent neural network but in code. Okay. And we will, so here we will start with data set. It will be bigger than one word hello, yeah. And here we simply upload all the data from file to the memory and create some helper objects. So you see this is chars object, which simply has all the characters from data set. This is set in Python. It means all the unique characters from the data, yeah. And then we simply put them into list to have order, so to have numbers for each letters, yeah. Then we calculate data size and the size of vocabulary. It means the size of the amount of all the characters in data set and the amount of unique characters in our data set. And so you see 173 unique characters. And here we create two dictionaries, two Python dictionaries. So the first is character to index, which is simply numbers of characters, yeah. And the second is vice versa, index to characters. So if we use second, then we can print characters based on their indexes. Okay, and here this is the first about 600 characters from the data set. So you see some book about St. Petersburg mathematicians and their discoveries, and you see mostly English letters inside, yeah. So this is our data set, and if we join with space all the unique chars from the data set, we will see so different English letters, some Russian letters, also Cyrillic letters, and some even Unicode. But it's okay. So it is not very important for us because we simply want to have the dictionary with all the characters from the data set, and we want to number them, so order them and number. Yeah? So we will train our model based on the data set, and the characters represent all the data for the model. Okay, now we go on to the initialization of all the parameters. So this is hidden size, the length of h vector. Yeah. Then we need to specify sequence length. So when we let me show you again the slide with structure of network. So here you see 4 steps, yeah, and previously the recurrent neural network has some amount of states, yeah. So this is the sequence length. So how many letters we use to predict next one, okay? Or not how many letters. So how many letters we use to update the hidden layer and then to predict the next step. Yes, so this is the parameter for architecture. So we should specify the maximum amount of steps, yeah, for our recurrent neural network. Okay, and of course we learning rate. This is the usual standard parameter for stochastic gradient descent method. And now we go to the initialization of so the init values of the model parameters. Each parameter lies in some 2-dimensional matrix. So the first matrix wxh, then the second is whh, the third is why. So they project the correspondent vector. So for example, why projects h vector to y space, to the vector y in our space. And you see the sizes of matrices is pretty clear. So from x to h, it means, yeah, vice versa, yeah, from h to x. We want to, oh, no, the x have the cap size length, and we project x to h, it means that the output size of the matrix multiplication will be hidden size. Yeah, and also here we add some bias vectors. You see the BH bias for H vector has the same dimension, the same size as hidden size vector, and the BY has the lookup size because we add BY to the result of multiplication, yeah, WHI and H, so to the final result. Okay, and so we will use all these parameters for train loop. And now we need to specify some loss function. So here this is, yeah, forward path for loss calculation, and firstly we here we compute all the raw scores. Yeah, so for each letter we compute 4 or more. So for this data set we will compute 173 scores for each class, one score for each class, and this is F, yeah, and softmax of these scores will be probabilities for each classes. And here we need to understand what is going on. So the loss function is minus logarithm of the probability of ground truth label. Yeah. Okay. Let me switch to the whiteboard and to explain what's going on and why the partial derivative, so the derivative of loss function with respect to raw score F, will be this number. So pk minus 1 multiplied by the characteristic function of yi equals k. So it means if k equals ground truth label, then we want to subtract 1. And if it doesn't equal the ground truth label, we simply put p, so the same probability pk to the gradient of loss function with respect to f. Okay. Let's dive into the formulas and understand what is going on here. So yeah, great. So our recurrent neural network, on each step we get the vector of scores, so f1, f2, and so on. Let's say f173, yeah, for this data set. For each class we have on one score, one evaluation score. And this is the result, actually, the result of multiplication, yeah, the matrix WHY with current hidden state, yeah, current hidden state H. Then we calculated the probabilities. So we use softmax function to calculate vector of probabilities P1, P2, and so on, P173. And each probability here, so each probability Pk is simply the exponent of Fk, yeah, exponent of Fk divided over the sum of all other all the exponent F j, yeah, j goes from 1 to 173. So for all the score evaluation, yeah, scores evaluation. Great. And now we want to calculate loss. Yeah. So we know here we have only vector of probabilities. Yeah. But it comes from the initial input x, y. Yeah. So here we have x, y as input. But of course, with x, y, we have also ground truth answer yi. Yeah, this is ground truth. And this is some number from so the number of right class. Yeah, it lies from 1 to again 173, because this is our number of class and it is integer value. So the loss function, let me switch to blue color. The loss function, yeah. Yeah, f are numbers. It is the results of matrix multiplication of hidden state vector and the matrix of parameters w, h, y. Okay? This is the output. Yeah. Yeah, H is current hidden state of recurrent neural network. Let me switch back to the to this picture here. So H, for each t we multiply ht on the one and the same matrix of parameters, yeah, w, h, y, and it gives us each iteration gives us the vector of scores. Okay.
And v h y is just linear layer to convert it to like probabilities of classes. Okay.
Yeah, it's just linear layer.
Oh, yeah.
So we
Okay.
it is linear operation of of multiplication h with w, and this is our raw scores. Yeah. And here you see the yi is ground truth label. So this is label of class. It is important here. So it's not the vector. It is one number. Okay, so now we want to calculate the general loss. So for this step, we know the ground truth label, yeah, and we know the probabilities. And loss function is okay, let me write it here. So loss function is cross entropy loss, because this is classification task essentially, yeah. So loss is cross entropy of the p of the probabilities of the vector of probabilities, yeah, and ground truth answer yi. Okay. And actually the cross entropy for these answer yi, so it means that we can consider two vectors. So the first is vector of probabilities from the model P1, P173, and the second vector is binary vector with one only on the component, on the number of right classes. Yeah, so this is yi place. Okay, yi place. So not first, not second, but yi. Okay, something here. And we want to have our probabilities as close to this vector of probabilities as possible, because this is our ground truth answer. Yeah, so we want this is true answer. We want our probability distribution to be as close to this probability distribution as possible. And it means, so the cross entropy, usually we multiply the ground truth probabilities. Yeah, let me remind the formula from previous from previous lecture, and the formula of cross entropy loss was like minus sum of multiplication, yeah, q, let's say qj multiplied by logarithm of pj, yeah, with all the j's from 1 to 173. And this is general cross entropy loss. But for our problem, the q probabilities are binary values, so they are only 0 and 1s. That's why from this sum we will take only one term, yeah, and this term will be simply minus 1 times logarithm of p with index yi, yeah, so with index of ground truth class. Okay, this is our loss function. So, and now we want to calculate the gradient, so the partial derivative of loss with respect to all the parameters. And that's it means that we want to calculate the loss with respect to all the f, let's say k, so for different k, yeah, so k from 1 to 173. And so let's do it, yeah. So we know what is loss, so here the partial derivative of loss with respect to fk, and loss is minus logarithm of p yi, yeah. And actually the we know what is p for each, so we know what is p for each index, yeah. This is the formula for p. It means what we need to, so let me write here, so the loss from fk, yeah, so this is pk, and I want to change this, so this is only one index yi, and I need to calculate partial derivative for all the components, for all components. And yeah, that's why here I can write so I will change, I change yi, some certain number, to the j index, okay. And so it means that I will calculate, so the so the partial derivative with respect to fk, yeah, from the minus logarithm of probability, and probability is let's say it will be pj, yeah, pj probability, it will be minus log of exponent of f j, yeah, divided over sum of the exponent of f. Here I can use any index j, k, let's say m, yeah, so this is fm for m from 1 to 173, okay. So this is our task. I want to differentiate this function with respect to fk, and of course there are two possibilities, yeah. So the first possibility, that here in numerator I have the same index k as in the derivative, yeah. So here I will write k equals j, yeah. And the second probability if k is not equal j, okay. Maybe let's start with the most simple case. So here k is not equal j, and here k is equal j. Yeah. So when we perform forward pass, the answer is yes. So j is equal to yi if we know the ground truth label. Yeah. But in general, then we want to calculate all the derivatives. It is not equal to yi because we want simply to know all the answers. Okay. So for all the components of the it means for all the probabilities, yeah. So this is minus log of probability, and here we have all the probabilities, yeah. P1, P2, and so on, and we want to differentiate them all with respect to fk, okay. And the first case, if k is not equal to j, then in numerator we have no the same variable, yeah, fk, and fk is only in denominator. It is easy for us because we can, so this is equal to, and the first case, we simply differentiate all the function using chain rule, yeah, so step by step. The first step is differentiation of logarithm, yeah, so derivative of logarithm with respect to fk. Then we need to differentiate the argument of logarithm, and it has fk only in denominator. So let me write it. The derivative of logarithm is 1 divided over argument, yeah. It means the sum of all the exponents fm. Let me skip indexes. So and I need to preserve minus, yeah, and the nominator is exponent of fj, yeah. And then I multiply this result of the derivative of logarithm to the derivative of the argument, yeah. And again, the derivative of argument is so something divided over sum with fk inside, yeah. It means that I want to differentiate inverse function, yeah. So this is the sum of exponent to the power of -1, and the result will be minus before the result, and then the same denominator, yeah, in the second power, so the exponent of fm, sum of the exponent squared, yeah. This is the derivative of so let me say x to the power of -1, yeah. So minus x to the power of -2. Of course, the numerator is not changing because k is not equal to j, yeah. It is constant for fk. And the last part is the derivative of sum, yeah, the derivative of sum with respect to fk. And of course, only one term depends on fk. That's why the derivative of sum will be the derivative of this one term, and this one term is exponent of fk. And we know that the derivative of exponent of x with respect to x is the same exponent of fk, yeah? The same exponent of fk. That's it. So we go through all the derivatives, yeah? And now we can simply put everything back. So looking at the result, you see minus and minus will be plus, yeah? One sum, and here one sum will give us only one sum in the denominator, then exponent of fj and exponent of fj here, they are annihilating 2, and the result is simply, you see, exponent of fk, yeah, divided over sum in the first power. So the sum of all the exponent of fm with m from 1 to 173. And you see, what is it? What is it? So exponent of k divided over sum. This is exactly the p, yeah, the probability pk, the probability of k component. Okay, so this is exactly pk. Then k is not equal to j. And let's go on. So we will now differentiate the same loss function. Then k is equal to j. Yeah. Let me change color second time. So if k is equal to j, then we want to differentiate the loss function by dfk, and k and j is the same. And the formula now is, so the derivative with respect to fk from the minus logarithm of exponent here should be fj, but this is j is equals to k, so I will write fk, yeah, and divided over sum of exponent for all fm, yeah, sum over m. Okay, so the at the beginning the result is the same. It will be minus sum exponent fm divided over exponent fk, yeah. Then we so this is the derivative of logarithm. Then we need to differentiate the fraction, yeah, the nominator and denominator, which both have fk inside, yeah. And the formula of derivative for the, let me write it here, yeah, the formula of derivative for the fraction f divided over j is the derivative of f, yeah, of nominator times j minus f times derivative of j divided over j squared, yeah. So this is formula of of derivative for f divided over j. And here we need to do it. So the result is the derivative of nominator, yeah, it is exponent of fk, and we differentiate with respect to fk. So the result is again exponent of fk, yeah. Then we multiply on j, and j is sum. Let me simply write sum, yeah, without any. So sigma is sum. Then minus f, this is exponent of fk, multiplied by the derivative of j, and j is sum of all f's, yeah, the exponent of all f's, and the derivative of all the sum is simply the derivative of one term inside, and this one term is exactly exponent of fk again, yeah. So here we have second exponent of fk in the nominator, and the denominator is simply j squared, so this is sum squared, yeah, sum squared. Okay, and now let's go on to, this is the final result, and again we can get rid of sum, yeah. Of course we can get rid of exponent of k here and here, and the result is minus, let me put it like this, sum minus exponent of fk, yeah, exponent of k divided over sum. And here I need to divide, so it will be, yeah, minus 1 plus exponent divided over sum. And I will change the order. So exponent of fk, which is the same as fj, yeah, divided over sum of all the exponent of fm, and minus 1. Yeah, this is the result. And again, what is exponent of k divided over sum? It is simply the pk. Yeah, so the result here will be pk minus 1. And in general, so if we, so let's combine two results. Yeah, so for case when k doesn't equal to j, the result is simply pk. And then k is equal to j, the result is pk minus 1. Okay, it means that our first formula in Jupyter notebook, which is d loss by dfk, is exactly pk, so the same vector of probabilities as we've seen in output, yeah, minus 1 if the ground truth label yi is equal to k. Okay, so if the indexes of k and j are coincide, then we need to subtract 1 from the result. Okay, great. I suggest to have a break here for let's say 8 minutes, yeah, so till 5 p.m. and then we will continue. Of course, if you have any questions, please ask. Yeah, this is the result, so the final result of differentiation. Okay, great. So let's continue. We we proved that the derivative of loss function on the right layer, so because of logarithm and softmax, is pk minus 1 multiplied by the characteristic function of k equals yi, the ground truth label. And here is the loss function code. So this is essentially a forward pass through our network with all the matrices. So we start with set of x's, h's, so hidden states, y's, and probabilities, and we copy previous hidden state if it exists, and the loss is 0, so the initial loss is 0. Then for whole range of inputs, so for each character, we firstly encode character to the one hot representation. Okay, so this is x's, and the t component. The xst will be zeros except one component, which is the number of current letter. So inputs from t is the number of current letter, and we put 1 to this component. Then we perform recurrent cell operation. So here you see 10h of dot product of x's, so this is the current letter embedding, and the parameters matrix, w x h. So we project x's to h's, so the next hidden state, and we add dot product of w h h with previous hidden state, so h is t minus 1. So the exact formula as we've seen on the slide, and then we apply activation function 10h to get the current hidden state. We use current hidden state hs to predict scores of the classes, so y's is our current scores, and the probabilities here, so you see the softmax formula. So the probabilities here are exponent of xs of y's divided over sum of all the exponents. Okay, and and this is all the probabilities for next characters. And we update the loss value, adding minus log of probability for true label class. So this is again targets of t. It is current ground truth label number, and the so we put we take only probability corresponding to this ground truth label, and then we add minus log of this probability to the loss, and essentially it is cross entropy loss. So, and this is the end of forward pass. Now we go to the backward pass. So we need to compute gradients going backward. And firstly, all the gradients are zeros, so numpy zeros, like for each matrices and biases, so vector of biases. And even so, the initial state, so the leftmost state of our recurrent neural network is vector of zeros. Okay. And then we are ready to perform backpropagation. So the gradient of loss function with respect to scores here, it is simply our probability. So this is pk's, pk's, all the probabilities. And then we subtract 1 only from the probability of ground truth class. So and here you see this is very very intuitive. So we understand what is going on. We want this. So in general, we are going to the anti-gradient direction. Yeah, it means that we want to increase only this probability of ground truth label class. Yeah, and we want to decrease all others. And here, if we subtract 1 from the probability which is between 0 and 1, yeah, it means that in our probability vector now all the probabilities will be positive except this one, and it will be negative. And minus this vector is vice versa. So all the wrong components are negative, yeah, and only one correct component is positive. So it means that we want to increase the score of this correct component. Okay, so the evaluation of correct class. And then we back propagate the same logic, we back propagate all the gradients to other parameters. So not only y's, but using y's, we calculate the gradients of why's and the bias y, and then the gradient of, again, loss function with respect to hidden state, because we need to train also hidden state, yeah, it's one of our parameters. And yeah, then we go to the all other gradients, so backward. And in the end of this loop, here you see we update these parameters. So all only these parameters which we are updating. So WXH, WHH, WHY, and biases. So three matrices and 2 bias vectors. And for DH and DH next, we only use them for calculation. Yeah, so we don't update anything except parameters in our model. Okay, and the end of function return current loss with all the gradients. Okay, which we want to know to update parameters on the next step.
What does np.clip do?
Yeah, what?
What does np.clip do? Like
Yeah,
after
numpy
in
dot.
in loop 4. No, not numpy dot. In a
Oh,
4
numpy clip. Yeah, clip is
mitigate.
simply clipping. So it means that so after clipping, the maximum value of parameter will be 5, the minimum will be -5, and if the value doesn't lie in this segment from -5 to 5, we simply clip it to either minimum or maximum. Okay, and we save only parameters between -5 and 5, and so this is simply other words. It is the the maximum, yeah, of
Don't have a big gradient, right?
And yeah. So to decrease gradient, so the maximum of -5 and d param, and then the minimum, yeah, of this value, and 5. Okay, so if it's greater than 5, then we simply reserve 5 as the final gradient. Yeah, so the final gradient. Okay, and that's it. Now we go further to the sample. This is simple function to generate new characters. So the logic is it is almost one forward pass, but here again the beginning is the same. Then for each, so for range and for each t, we simply perform forward pass. Yeah, this is the inference, and then we choose next character. So based on the current probabilities. Okay, so we use current probabilities as random die. Yeah, random dice, and each characters has some probability to be sampled, yeah, and the result is simply some new letter. We add this new letter to indexes, and then after n iterations we return the result. So this is simply actually inference of our model. Here is no any gradients, you see, and no any updates of parameters. And here is the main loop of training. So firstly, again, we initialize all the parameters as actually, so yeah, we not all the parameters. Here we initialize the memory of parameters, because here we want to use not stochastic gradient descent, but we will use the adaptive gradient descent, so the adaptive gradient method. And that's why we store the sum of all the gradients in these, actually the sum of squares of all the gradients in these variables. And now goes the training loop, so the main cycle. While true or while some number of iterations, we firstly prepare inputs. It means that we have, so for our data, we simply choose the segment of this data, so from P to P plus sequence length. Yeah, this is the inputs, so the 25 characters. And our targets is simply the same segment shifted to the right, because for current letter the answer is the next letter. Yeah, that's why we simply shift our segment to right, and it is our targets array. After these operations, so you see here our dictionaries mapping char to indexes, because of course we want to use numbers inside the model, not letters, not chars. And here sometimes, so if n divided over 1000, we sample from current model, it's simply printing. And here you see, so forward pass, yeah, loss function gives us all the gradients and loss for current batch, for current group of objects, inputs and targets. Yeah. Then we here print the result, the number of iteration and loss, and perform perform updating of parameters using these gradients. So here you see, because of adaptive gradient update, we go not to the direct anti-gradient direction, yes, so not only minus learning rate times d param, but this is the adaptive gradient denominator, yeah, addition. So we divide over square root of memory, and memory is, you see, the sum of squares for all the previous iterations. It is called adaptive gradient, and it is very similar to stochastic gradient descent, so the goal is the same. We update parameters to decrease loss function. And then we go to the next iteration. So here yes, you can run it yourself, but for simplicity, I will show you. So this is result without any train. So from first 1000 iteration, you see random letters. Yeah, so some random letters and random characters. Then after some iterations, model begins to put spaces. Yeah, so R, N, so it learns how to predict spaces, yeah, between words. Then, and you see loss is decreasing. Okay, so 91, then we see 774 and so on. So it's decreasing, and let's go to the end of the training loop. Yeah, so for example, after 100,000 iteration, loss is 46, so all is working. And you see the model generate something similar to English language. So you see the word there, and we can write it for their Pioneer's genes. So it is similar to English language, yeah, even for this very simple model and for not so huge data set. But we can generate text very similar, which is very similar to the original one, okay? And of course, this is amazing. So very simple model with simple updates. Simple update step, and of course, changing the data set, you can model different domains. Let me show why it works, or how does it work, and what is going on. So we have in our model, essentially we have only one vector of hidden state, yeah, one dimensional vector, and the three matrices of parameters, yeah. And actually you can check. So this is the result for LSTM model. It is slightly more complex than the vanilla neural network, recurrent neural network cell, but the logic is the same. So it has some hidden state vector inside, and one of the neurons, of the component of this vector, specialize on remembering if it is inside or URL or not. So you see the activation function of this neuron, and it is green color, yeah, then we are inside the URL, okay? So and this is so-called mechanistic interpretation, yeah? So we understand for different texts what is going on and how model works, yeah, works inside. Then we can find other neuron which gets very excited when we are inside the square brackets markdown. So you see again it activates, then we just inside the brackets, okay? And so it even must wait for the second bracket and then activate, because we want to, and of course it is likely that there is other neuron, different neuron, which which counts for brackets, and we can distinguish if we see only one square bracket or two, yeah. And even this simple model can predict the different properties of texts. So for example, of course, we need to predict the new line character, and here we want to close quotes, yeah. If we inside, then again we need to want, so some neuron should want to activate to close the quotes, yeah, and so on. So for each property of text, the model should be able to grasp it, and actually the model decides itself, yeah, which properties is better to predict to be able to solve the general task. And general task is pretty simple, simply predicting next character, yeah, next character, even not word, next character in the text. Okay, so now I suggest to skip long short term memory, because yeah, it is more complicated, but the idea is the same. So you simply change your recurrent cell with some more complex cell, which now has two vectors, yeah, so the same hidden state vector, and we add new content state vector, so, and we update them both, and the idea is that network should remember the context for a long time, so not only for 25 characters inside our sequence length, but for some long context. And which context the network learns itself. Yeah, so that's why we introduce the new context vector C. And for other versions, so-called GRU or gated recurrent unit, again we perform some other operations, but the idea is the same. We have hidden state vector, we have some formulas, and we predict scores based on this hidden state vector, and we update state of the system, state of the unit inside our model. Okay, and here vector C even is not introduced. So that's why the GRU is a little bit more simple, but the effectiveness are almost the same. So you can interchange LSTM cell unit to GRU and vice versa if you want. And the last slide of the lecture, so it is for the attention mechanism. So what are the problems, disadvantages of this recurrent neural network approach? Yeah, both for vanilla recurrent neural network or LSTM or GRU. So the input and output signals lengths must match. Yeah, so because for each X we predict Y. Okay, that's why. So the length of two signals must match. We read the input only from left to right. Yeah, this is the second disadvantage, and we cannot look ahead. And sometimes it is useful, yeah, to look ahead. For example, in machine translation task. And yeah, so it is not suitable enough for machine translation, for different question answering tasks, and so on. And the next step after the recurrent neural network was so-called encoder-decoder architecture. And the idea is pretty simple, and it is almost, so it is like two RNNs. Yeah? So the first RNN is encoder, and we perform the same operations, but our answer is only one vector C. And this vector should remember all the input. Okay, so the goal is to get all the input inside one vector C. And then we put this C as input to the decoder part. Okay, each time instead of X's, we feed C, one and the same C, to each step in decoder, and decoder generate, for example, machine translation from one language to another. Okay, so these are different spaces. So the space of English language for encoder and the space of Greek language for decoder. But inside encoder-decoder, it is simply either recurrent neural network vanilla cells or LSTM cells. Okay, and we update states and we predict Ys, and then we apply softmax to get probabilities of each tokens. Actually, the terms inside sequence are called tokens. So so sometimes it's not characters. It may be, it should be part of words, yeah, or even words sometimes. But yeah, the general term is token. Okay, and that's it for today. Yeah, so we discussed recurrent neural networks as simple and flexible approach to solving various machine learning problems. We dive into vanilla RNNs and a little bit touch to LSTM and GRU, but not in details. Yeah, and that's it. So now you can use this simple model to generate any stuff. And in the blog post of of Andrei Karpathy, you can find very, very impressive examples of generating, I don't know, C code of Linux, Linux core, or generation of the uh, uh, mathematical proofs, yes, of the text which are in TeX, in LaTeX, and they are very similar to mathematical proofs, yes, of the even this simple architecture as LSTM can grasp the structure of, for example, C language, or structure of LaTeX text from mathematicians. Of course, they are useless and they have no any sense inside, but the syntaxis, the structure is usually correct. And yeah, so of course there are many open questions, but now after this lecture we are close to the next step, and the next step after encoder and decoder will be attention mechanism and transformer architecture. And transformer architecture is already the workhorse for all the current modern LLMs, so large language models, which you have heard
Question.
about, I'm sure. Yeah, sure.
Train RNN. We have. Am I right that we have like length of sequence, some constant, and it's like, is it like batching, or why do we need it? Like
Here, so our batch here is the inputs and targets. Yeah, so the question is about sequence length.
But if we have LSTM, does it like does our SQL sequence does it influence like training? If for LSTM we should remember long uh some long dependencies. So
So
does it matter?
for
Like,
LSTM, the logic is just the same. So you simply change your one formula. So for vanilla RNN, you you use the linear layer. Yeah, let's say this is simply linear layer with activation function, and this is your vanilla recurrent neural network cell. Yeah. And in LSTM cell, you change only these to some other formula. So this one, yeah. So you take two vectors, C and H, but you again, so started from previous hidden state, yeah. You update everything and get the current hidden state, okay, HT, and then you predict YT based on this current hidden state. Except this cell, nothing is changing, okay?
okay.
So
And for
it
like for decoder and encoder, like in decoder we put our C, so like our C what is it? Our C vector as
as
in
axis,
encoder, could you,
yes.
yeah,
So for decoder,
as
we
axis, yeah.
yeah.
So for
We
all
use
like
as
for
axis.
all hash iter until we generate something like end of sequence token,
Yes,
right?
Then we generate end of sequence token. That's right here. And here, so the
Okay.
cell inside could be vanilla RNN or LSTM cell. So for predicting next, for getting next state, yeah, next hidden state vector, H, or G rule cell, yeah. So one of three variants.
Okay, thank you.
Okay, great. Any other questions? Okay, great. And thank you for your attention, and see you next week. Yeah, have a nice evening.